A single YAML typo, one missing selector, can cause hours of downtime. Your cluster isn't just messy, it's a ticking time bomb. This video is your escape plan from that endless firefighting loop. Think of Kubernetes as a giant crane at a busy container port. Each shipping container is an isolated app environment. That's your Docker container. A pod groups containers that need to share network and storage, and the crane, Kubernetes, decides which machine each pod lands on, keeps it running, and replaces it if it crashes. The tool you'll use to speak to the cluster is kubectl. That's orchestration in under 30 seconds. A modern e-commerce site might have 12 microservices, each with 3 replicas. That's 36 pods, just to meet baseline demand. During a Black Friday sale, auto-scaling kicks in, and you can easily hit 150 or more pods. Managing that sprawl by hand is where the nightmare begins. When you try to manage microservices with raw kubectl apply, you end up copying YAML files and running 15 separate apply commands, praying nothing breaks. The classic mistake: updating a deployment label but forgetting to change the matching selector across 10 other files. Result? Your front end silently loses the back end while traffic still flows to nowhere. Helm fixes this with one command and templated selectors that stay in sync. Plain manifest management has 3 fatal gaps: no history, no one-click undo, and no templating. Helm, the package manager for Kubernetes, solves every one of those. With a single chart parameterized by overridable values, you can reuse the same package in staging, production, or any environment without rewriting manifests. Helm history gives you every revision, and Helm rollback lets you quickly revert to a previous, known good state. These 3 commands alone eliminate hours of manual toil. Time for a checkpoint. First question: what are the 3 major pain points of managing Kubernetes manifest without Helm? And second, what are the key components inside a Helm chart? Pause the video if you need a moment. Answer: without Helm, templating, release history, and rollback are difficult and error-prone. A Helm chart contains templates, values, .yaml, and chart metadata. Another checkpoint: what leads to a proliferation of pods in a Kubernetes cluster, and what tool can help manage them? We'll see. Answer: when you have many microservices, each with replicas and autoscaling, it can lead to hundreds of pods, often called container sprawl. Helm charts help package versioned deployments so you can manage them as coherent releases. Helm is the apt, or yum, for Kubernetes. It packages a complex application, think WordPress, which used to need 6 manual steps, into a single versioned chart. One Helm install command and the entire stack deploys, with all dependencies sorted. It's how the open source community shares battle-tested configurations, and it's what we'll use from now on. The best resource? The official Helm docs at helm.sh. Let's dissect a real Helm chart. Chart.yaml holds the chart name and version, your release history. Values.yaml is where you set defaults like the image tag. The templates folder contains the Kubernetes YAML files, but with Go template placeholders. When Helm renders a deployment, the Sombr values image .tag gets replaced by whatever you specify. One blueprint, many environments, 0 copy-paste. Installing Helm is 3 straightforward steps. First, download the official get-helm.sh script with curl. Second, make it executable and run it. Third, verify the installation with Helm version. Do this now, and you'll be ready to deploy your first chart in the next scene. A Helm chart is a reusable package of Kubernetes YAML files, like a recipe for your app. The command helm create myweb scaffolds a minimal chart, giving you a templates folder and a values YAML file. By editing values YAML and setting replica count to 3, you tell Helm you want 3 identical pods running. Then a single Helm install deploys the packaged app, and watching kubectl get pods confirms you just slid from 0 to a live, load-balanced Nginx service, all without handcrafting multiple YAML files. Helm uses Go templating, so you can override values at install time. A cheap staging-only deployment uses set replica count 1 service.type cluster IP. For production, a separate values_prod.yaml file sets replica count 8 and service.type load balancer. Look at the highlighted line. A beginner trap. Hard coding. A load balancer service in the chart's default values spins up a cloud load balancer in staging, and you won't notice the accumulating costs until the end of the billing cycle. Always keep defaults safe and override for production. Quick knowledge check. If you've been following along, you should know the answer to this one. What flag allows you to override a chart value directly on the command line? Helm treats each deployment as a release, a named versioned instance of a chart. Running Helm list shows all releases, their revision number, and status. Helm upgrade applies changes to the existing release, updating the revision and leaving the history intact. The power move is Helm rollback. If you realize the upgrade broke something, one command reverts to a previous known good state, all as a single lifecycle operation, no manual YAML surgery. Imagine deploying a new version with a bug that starts returning 500 errors. Instead of scrambling to revert, Kubernetes manifests manually. You run Helm history myapp to see every revision, then Helm rollback myapp to quickly revert to the previous release. Within seconds, Helm recreates the old pods from that revision, and your customers barely notice. That's not just a time saver. It can be the difference between a 5-minute blip and a multi-hour outage during peak traffic. Here's the full pipeline. A developer pushes a Helm chart change to Git. The CI pipeline packages it and pushes it to an OCI-compatible registry. That's a standard container image registry used for Helm charts, like your cloud provider's container registry or Docker Hub. Argo CD, watching the Git repository, automatically syncs the new revision to your Kubernetes cluster. If the new version causes issues, a simple Helm rollback restores the previous known good release from Helm's own revision history. The whole pipeline turns infrastructure changes into code, fully version-controlled and auditable. Helm hooks are resources, often jobs, that run at specific lifecycle moments like pre-install, post-upgrade, or pre-delete. Here the annotation helm.sh hook pre-install, pre-upgrade tells Helm to fire this database migration job before any application pod starts. That means you never have to remember to run a manual SQL script after deploying. Helm choreographs the whole sequence. Run the migration, wait for it to succeed, then start the new pods. It's the glue that turns a dangerous manual step into a zero-touch deployment. Quick recall. If you followed the Helm hooks example, you should be able to answer, when you set a pre-upgrade hook, what exactly happens during a Helm upgrade? Think of a service mesh like a factory supervisor who stands right next to every worker on the assembly line. Istio injects a tiny proxy, called Envoy, beside each of your application containers. That proxy takes over all network traffic. It retries failed calls, encrypts them with mutual TLS, collects metrics and traces, and enforces access policies. All of this happens without you changing a single line of application code. It's the infrastructure layer that upgrades your Kubernetes cluster from a chaotic workshop into a tightly monitored, secure production line. Here's the magic. When you label a namespace for Istio injection, Kubernetes automatically adds an Istio proxy container to every new pod. That Envoy sidecar intercepts inbound and outbound TCP traffic using iptables rules. Your app still thinks it's talking directly to another service, but in reality it's talking to its own local envoy, which then uses MTLS and retries when it reaches the other side. This architecture means developers write zero extra code. They just deploy, and the sidecar takes care of the entire east-west communication layer. But here's the part almost everyone gets wrong about service meshes. They don't just add encryption. They replace your retry logic entirely. On the left, a developer is handwriting retry loops in Python, duplicating that code across a dozen services. It's brittle, and every tweak needs a new deploy. On the right, Istio's virtual service retries failed calls and enforces timeouts centrally. No code changes. Circuit breaking is configured via destination rule, but together they decouple network logic from business logic, exactly the way cloud-native apps were meant to be built. Observability is often bolted on after an incident. With Istio, you get it for free. No import statements, no tracing libraries. The Envoy sidecar sees every request and response, so Prometheus scrapes metrics, Jaeger traces each hop, and Kiali draws a live map of your services. After you label a namespace, these dashboards light up automatically. Later, you'll open Kiali and watch traffic flow in real time. For now, remember, metrics, traces, and a live service graph. 0 lines of new app code. We need a realistic target, so we'll use Google's Online Boutique, a microservices app with 11 different services, a web front end, a cart, a checkout, product catalog, shipping, and more. This is our messy, unmeshed cluster. The perfect playground to see what a service mesh actually does. Time for a quick checkpoint. After installing Istio, what are the 2 main components of Istio's architecture? Pause. If you said the control plane and the data plane, you're right. The control plane, primarily Istioed, manages configuration and policies. The Envoy sidecars in the data plane handle the actual traffic routing. Knowing this separation is key to understanding Istio. Time for the magic moment. Label the default namespace with Istio injection enabled. That single line tells Istio to modify every pod spec at admission time. Then delete all the pods. The deployments recreate them instantly, but now each pod gets a second container, the Envoy sidecar. Run a describe and you'll see Istio proxy alongside your app. From now on, all traffic passes through the sidecar, giving you observability and encryption for free. To open the Kiali dashboard, first run kubectl port forward, SVC Kiali 2001 and Istio system. Then navigate your browser to HTTP localhost 2001. You'll see a live map of all your microservices. Every line is a request, color-coded by HTTP status, green 200, red 4x or 5xx. Click, zoom, and watch the traffic flow. All this telemetry comes from the Envoy sidecars you injected earlier, not from code you wrote. That's observability for free, and it takes less than 5 minutes to unlock. Checkpoint time. What single label enables automatic sidecar injection in a namespace? Pause. Istio injection enabled. Once that label is applied, every new pod in that namespace gets an envoy sidecar automatically. You can verify it with kubectl describe pod. Look for the Istio proxy container. That one label is the key to observability and MTLS without touching your app code. CRDs, or custom resource definitions, are Kubernetes extensions that let you define your own API objects. In this case, Istio defines two fundamental CRDs, virtual service and destination rule, that handle most routing logic. Virtual service acts as a routing map. It decides where requests go based on weights or headers. Destination rule then applies policies like load balancing and TLS to the selected subset. A classic beginner trap. Defining a virtual service without a destination rule. Your routing may silently fall back to defaults, causing unpredictable behavior. Always define both together. Treat them as a pair. Canary releases let you roll out a new version to a small slice of users. Here we define a virtual service with two subsets, V1 at 90% and V2 at 10%. Apply it, then hit the front end 100 times in a loop. You'll see about 10 responses from the canary. If V2 starts throwing errors, revert the weight to 0-100 instantly. No downtime, no panic. Traffic shifts in milliseconds because the sidecar respects the new rule atomically. A blue-green deployment flips your entire user base from one version to another in a single, atomic step. Once the green pods are pre-warmed and passing health checks, you update the virtual service to route 100% of traffic to the green subset. The envoy sidecar picks up the new rule immediately, so no request gets dropped. The key trap. Skipping the warm-up. Always run kubectl. Get pods, and verify readiness before shifting traffic, or users will see cold start latency. Downtime crushes revenue. For large enterprises, an outage is a financial disaster. Istio's traffic management, circuit breakers, canary releases, and zero downtime rollouts acts as your financial bodyguard. No more deploy at 2 a.m. and pray. The mesh keeps your service stable and your bottom line safe. What is the key advantage of mutual TLS over regular TLS in a service mesh? Pause here and think. The answer: it provides two-way authentication. Both the client and server prove their identity, so no rogue service can eavesdrop or impersonate another. A common pattern is to apply a peer authentication resource in the Istio system namespace with mtls.mode, strict. This tells the mesh to only allow encrypted connections between sidecars. Any pod that tries to talk in plain text will be rejected. To verify enforcement, try kubectl exec into a pod without a sidecar and attempt to curl a backend service. The connection will fail because the sidecar refuses the unencrypted handshake. Istio authorization policies give you surgical control over service-to-service communication. You can configure a policy that permits traffic only from the front-end namespace to the back-end service on port 8080, and the mesh denies everything else by default. In a real breach, a compromised pod from any other namespace that tries to reach that backend hits an invisible wall. No matching rule, no traffic. This kind of zero-trust segmentation requires zero app code changes. Kubernetes security is a stack, not a single silver bullet. Network policies restrict traffic at the IP port level. RBAC governs who can access cluster resources. Secrets management keeps sensitive keys out of plain text. App-level auth verifies user identity. Right in the middle, an Istio service mesh fills the critical east-west gap that native Kubernetes can't cover. MTLS encrypts pod-to-pod, and authorization policies lock down which service talks to which. Without the mesh, a single compromise can wander sideways unchecked. Pause right here. You've just learned traffic splitting and MTLS enforcement. Here's a quick check. Which two Istio CRDs control traffic routing and policy? Pause. Virtual service and destination rule. Virtual service says, send 20% of traffic to V2, and destination rule defines the subsets. Master those two, and you control the flow. But here's the part almost everyone gets wrong. The number one reason for production outages isn't a dramatic crash. It's a tiny failure that snowballs. Imagine the payment service starts returning 500s. Calls to it queue up, saturating the inventory service. Then the front end, waiting on inventory, becomes unresponsive. In minutes, the entire cluster is down. This cascading failure is exactly the nightmare that steals weekends, and it's exactly what circuit breakers were born to stop. This destination rule is your fuse. It limits the payment service to one concurrent connection and, more importantly, opens the circuit after 5 consecutive 5.5xx errors. For 30 seconds, the sidecar won't even forward requests. It fails fast, immediately returning a 503. That gives the struggling service time to recover without dragging inventory and front end down with it. Without this, every slow service becomes a ticking bomb. Transient glitches happen. A pod restarts and misses a request. With a service mesh, you can configure retry policies and per-try timeouts directly on the sidecar. Each attempt is bounded, so a small hiccup doesn't snowball into a retry storm that overwhelms your backend. And because the retry logic lives in the infrastructure layer, no application code needs to change. Kubernetes readiness probes are essential, but here's what a service mesh adds. Istio's sidecar watches those readiness signals and instantly removes an unhealthy pod from its load balancing pool. Without the mesh, a pod that's stuck but still technically alive might keep receiving requests even after you think Kubernetes isolated it. Because some load balancers or service meshes don't respect the probe. With Istio, the sidecar enforces health-based routing at the edge of every pod, making your probes not just diagnostic but truly healing. Here's the pipeline you've built. A developer pushes code, CI builds the container and pushes it to the registry. Helm packages the chart, the same chart you already templated, and deploys it with the canary values. The sidecar injector automatically inserts the proxy, and a virtual service gates just 5% of traffic to the new version. Meanwhile, MTLS encrypts every hop between services. Prometheus scrapes the mesh metrics, and if P99 latency, the 99th percentile response time, meaning only 1% of requests are slower, spikes past your threshold, the deployment auto-rolls back. All without a single engineer waking up at 3 a.m. Istio uses outlier detection to automatically remove unhealthy pods from the load balancing pool. When the Envoy sidecar observes a configured number of consecutive 5xx errors from a pod, it ejects it from the pool, stopping all traffic to that instance. This happens without waiting for a readiness probe. The sidecar reacts to real-time failure signals. So your circuit breaker isn't just a wall, it's an active ejection mechanism. Take a typical mid-size e-commerce platform as an example. Before Helm and Istio, they struggled with deployment-driven outages, averaging 4 incidents per month, each causing a 30-minute hit. After adopting Helm for immutable versioned releases and Istio for circuit breakers and canary rollouts, they cut incidents to less than 1 per month and recovery times to under 5 minutes. The bar chart shows that drop. the difference between firefighting and sleeping through the night. Checkpoint. What does a circuit breaker prevent? Pause. A circuit breaker prevents cascading failures. When a downstream service starts timing out or returning errors, the breaker opens and immediately returns a fallback response instead of piling on more requests. This buys the failing service time to recover, avoiding the thundering herd that can take down your entire cluster. The eternal tug-of-war ends here. Developers want velocity, operators want stability. Helm gives developers a repeatable, auditable deployment process with instant rollback. Istio gives operators a programmable network that enforces rules automatically. The result: devs ship fearlessly, ops sleep through traffic spikes. That's what we mean by a sane production platform. Run-in full replicas 24/7 burns money. With Istio's traffic shifting and Kubernetes horizontal pod autoscaler, HPA, which scales the number of pods based on CPU or memory, you can schedule the mesh to route non-peak traffic to fewer pods. This line shows CPU with precision routing. Notice the drop during off hours. Without the mesh, you'd be running at a constant high replica count, wasting compute capacity that could be scaled down. Multiply that across a dozen microservices, and the savings become material immediately. 6 tools. That's the whole arsenal you need to go from zero to cloud orchestrator. Kubectl speaks to the cluster, Helm packages the apps, Istioctl debugs the service mesh, Kiali gives you a real-time map, YQ makes YAML programmable in CI, and Git keeps history so you can always rewind. If you only install one new thing this week, make it YQ. It'll save you hours of manual YAML editing. When you package your app with Helm, you can include Istio resources as templated manifests. A chart can conditionally create a virtual service that switches traffic to a canary subset, and a destination rule that enforces MTLS with circuit breakers, all based on values. This turns an entire deploy with mesh routine into a single Helm install that's versioned, repeatable, and Git controlled. Checkpoint. What's a common Helm pitfall that can accidentally expose internal services? Pause. A simple mistake like leaving service.type, load balancer, in a default values.yaml can suddenly give an internal backend a public IP. Always maintain a dedicated values.prod.yaml and run helmlint before every deploy. That one habit has saved more midnight pages than anything else. You've built a complete production workflow. Now deepen it with these 4 resources. CodeCloud's courses are the gold standard. If you only do one, pick the Istio one. It will save you months of trial and error. Bookmark the official Istio tasks. Page for copy-paste ready YAML. And schedule a weekend for Kubernetes the hard way. Once you've built a cluster from scratch, nothing feels like magic anymore. Finally, join the Istio community Slack so you're never stuck alone. Now picture this. Every Helm chart you've built lives in a Git repository, and a tool called Argo CD watches that repo. The moment you push a change, it reconciles your cluster to match, automatically. That's GitOps, and it eliminates manual kubectl apply forever. Combine it with Istio's multi-cluster support, and you can fail over an entire microservice to a backup cluster in another region with 0 code changes. That's the level of engineering where you stop being a user of the cloud and start designing resilient global platforms. A community Helm chart can deploy the entire Google microservices demo over 10 services in seconds. First, add the chart repository and update it. Then, a single Helm install drops all the deployments and services, and when you set Istio injection, the namespace is labeled so Istio automatically injects the invoice sidecar. Compare that to applying a dozen raw YAML files by hand. Helm cuts the work by an order of magnitude and gives you versioned, repeatable deploys. Checkpoint. You label a namespace with Istio injection, enabled, and deploy a new pod. It gets a sidecar. But any pods already running? They won't change. That's a critical detail. The label only affects future pod creations. If you need existing pods to get the sidecar, you must restart them or roll the deployment. Remember, the mesh isn't retroactive by default. Fire up Kiali, and you'll see a live graph of your entire mesh. Every node is a service, every edge is a call. Click the security overlay. You'll see a lock icon on every single connection, proving mutual TLS is active. Then hover over the front-end edge to watch requests per second streaming in real time. This isn't a static diagram. You're looking at your own deployment's nervous system. Checkpoint. When you're in Kiali's service graph and you see that lock icon, what does it tell you? Pause. The lock means TLS is enabled. The sidecars are encrypting the traffic between those services. If you don't see a lock after enabling peer authentication, that's a red flag for plain text traffic. So always verify the lock after applying your MTLS policies. This virtual service defines how traffic flows to your front end. The subset v1 and subset v2 labels come from a destination rule we applied earlier, mapping pod versions. With the weight set to 90 and 10, Istio silently sends one out of every 10 requests to the new version. No new pods, no redeploys. Just a kubectl apply fboutique canary.yaml and your canary release is live. Run multiple requests in a loop. Each curl creates a fresh connection, so no browser caching contaminates results. Over many iterations, you'll observe a distribution that matches your configured canary weights, confirming the traffic split is working as intended. Let's verify your understanding of canary routing. Imagine you have a virtual service routing 90% to version 1 and 10% to version 2. You fire 100 requests. Roughly how many responses come from version 2? The answer: about 10 responses. With a 10% weight, traffic splits proportionally, so about 10 out of 100 requests hit the canary version. Use istioctl proxy status and check invoice stats to see this in your own cluster. Now apply this peer authentication policy. The screen shows the YAML. Once it's in place, every workload in the default namespace must present a valid MTLS certificate. To prove it, spin up a debug pod with kubectl run debug, image radial, busybox plus .shior, curl, it arm oshiashio. From inside, run curl vethpt and yar frontend bors. The connection hangs and resets because the sidecar refuses plain text traffic. That's zero trust networking at the application layer, enforced transparently by the mesh, not by developer code. This destination rule sets outlier detection on the product catalog service. After applying it, simulate a crash. Kubectl exec deploy chash product catalog. Pkill f product catalog. The sidecar detects multiple 5x errors and ejects the instance. Istio stops forwarding traffic to it. Now when you curl the front end, the call to product catalog is short-circuited. Depending on your application logic, you may see a degraded page or an error. To provide a seamless user experience, you'd typically add fallback logic, like showing a cached product list. The mesh gives you the circuit breaker. Your code provides the graceful fallback. Resilience begins here, but a few lines of app code perfect the experience.